Good afternoon, everyone. Sorry for the delay. This is due to departmental visits by our participant and experts to mathematics department after 1:15. So that's the reason that there is a delay of 10 to 15 minutes. Once again, we restart our afternoon session, that is the post-lunch session. Actually, in the morning I said, in the post-lunch session, the first session will be for the open discussion, oblique interaction with the experts to the participants. But at that time, actually, I had some doubts on Professor Brende. So that's the reason that I fixed it in the first and his lecture in the second. So he concluded his work, what he's supposed to finish off. So now I am little bit modifying, slightly changing. So this is interchange now. The last session will be the open discussion, and in place of the last session, this will be the preponed session. Professor Brende, he will talk on fixed points.
In ordered metric spaces, so fixed point, coupled fixed point, and so on.
Yeah, same thing, no? Okay. I had doubt. I worked a lot of work. Fixed points, coupled fixed points, and tripled fixed points in partially ordered metric spaces. Professor Brende will speak about, and I think my research scholar Rashmi, she has done lot of work and is a part of her thesis also. So that's why in her thesis, you are also referred as a reference. So I would like to invite Professor Brende to deliver his talk and interact with the participants. Professor Brende.
Thank you. So there is a bigger event here. We are now a little bit small in comparison to the others. They pushed us here near the all will survive. So this time I want to speak about some other context in which fixed point theorems could be useful for applications. And the idea is to speak about these coupled fixed points, triple fixed points, and so on, multiple. Don't speak in detail about these topics, but just like in the other presentations, I would like to give you an idea of how we can always develop our theory to cover more aspects and more applications. And this is the main idea of my presentation. Gregg-Gush fixed point, it's a very interesting. Who studied this? Murthy? I had it in mind for a long time, but I was not able, I did not find time to have some insights in this. It's a very nice result. Gregg-Gush. Okay, what it's about? I promise you that I'll present you some words about this polemic between pure and applied mathematics. And here are the, I found the, so this was a great Russian mathematician, Soviet mathematician, Petrovsky. He wrote a beautiful book on integral equations. So one of the best books. We had it in Russian, in Romania. Unfortunately, it was not translated. I don't know if it was translated into English, but usually in Russia, maybe you know, some of you, At present, the American Mathematical Society is paying a lot of people just to translate journals which are published in Russian into English. So they contain very deep and serious mathematics, so the American Mathematical Society is doing this. They simply translate Russian journals. Russian do not care about this, so they write in Russian. Some now, the young people working in mathematics, of course they are publishing in English, but usually they publish in Russian. So this is a proof of the great value of Russian mathematicians, very serious mathematics. Even now, I don't know the number of journals, but almost 10 journals are translated from Russian into English by the American Mathematical Society to make them free, accessible to the people who are reading in English. And Petrovsky, he was a very special person. He said the following one in this polemic: what is important, pure mathematics or applied mathematics? And he said, don't discuss this question. They are equally important. And his argument is here. For if we would be dealing only with applied mathematics, then one day it will happen that we do not have what to apply anymore. So this, we have to do mathematics all the time, pure mathematics, to have what to apply. So this phrase is very important and encouraging us working in fixed point theory and applications to produce results, even if we don't can immediately show an application. So we just do results in pure fixed point theory, so theoretical results, and I am quite sure we someday will have the chance that some of the theory is applied in the problem. But it happens the reverse situation. From applications, we can get some suggestion what theory to produce. And coupled fixed point is such an example. I told you that originally the fixed point theory is coming from differential equations. Solving differential equations, this tool was extracted by Banach from the method Picard have used solving differential equations. So that's all. So the first fixed point theorem is inspired from application toward theory. Now we are usually going in the reverse sense. So we are going from theory to applications. Unfortunately, in fixed point theory, we are doing too much theory. So I have to be honest, I'm not happy with this. Sometimes we are doing too much theory, and sometimes some of these fixed point theorems are not relevant. In the sense, they just repeat. So they are not applied to unsaturated situations. So they are applied to saturated situations. And what we get is not new. It's just the repetition. So I just want to support Petrovsky's sentence by this situation I talked to you 2 days before, I guess. So it was a discussion, and I quote this great French mathematician, Dieudonné. Dieudonné means given by God in French. So Dieu is God, and donné is given by God. Dieudonné wrote a very nice book on mathematics, and in French is this title, to honor the human spirit. So he said mathematics is something that is honoring the human spirit. And in that book he recounts this story about another great mathematician, Jacobi. You should hear of him, and Legendre. Jacobi said that that some people consider that the unique aim of science is to honor the human spirit. And he said in French that a question for number theory is the same like a question regarding the system of the world. And this is the letter translated by me from French into English, and he's telling about Fourier's opinion. As I told you then, Fourier had the opinion that the main aim of mathematics is just the public utility, so to have immediately applications. And Jacobi says, no, he's not right, because the unique aim of the science is this very nice idea to honor the human spirit. And so he considers that a number theory problem is equally valuable to a question related to the universe system. And this was written more than 115 years ago. And he's right, because now, as I told you, number theory is everywhere in computer science. Here's the book. If someone is interested, this is the French version. It's a very nice music. In English, the translation is not very inspired, because this means to the honor of the human spirit in French, but here is translated as mathematics, the music of reason. I don't like this translation. So, coming back to our theory, our main aim here is to put theory versus application in fixed point theory, and to speak about how relevant its theoretical results. And I will show, I do hope I succeed to persuade you that sometimes we state a very complicated theorem based on several conditions, but in practice it solves very trivial problems, very simple problems, and its utility, if usefulness, is not relevant. And this is the case with the coupled fixed point theorem, and triplet and multiple and so on. I'm speaking, starting from these papers I produced 13 years ago, 12 years ago, on coupled fixed point theorems, and published, as you can see, in a very prestigious journal, Nonlinear Analysis. There were very well received papers, but in the end I realized that they are not extremely valuable. So what's the problem? So I said this problem of coupled fixed point theory is coming from applications. We have this system of differential equation. It's first order. U is the unknown and V is the unknown. And in the right-hand side, we have some expressions, nonlinear expressions, and also linear expressions. The same lambda for U and V, the same lambda for V and U, and you can see also the same lambda 1 and lambda 2 here. This is important. So this is a system of two equations, differential equation, depending on two unknown functions. And if we consider these boundary value conditions, we are working on the interval, I forgot to say, the interval 0t. So we are here. So we we are asking for these conditions, so the solution will be, let's say, at the same level. This means u of 0 equal u of t and v of 0 equal v of t. This problem, as we know, can be viewed in this way. A function u equal a function of u and v equal a function of v of u. And this is a coupled fixed point problem. And f, we convert in the usual way the differential equation into a integral operator form, and we get this this expression for f of u and v. You can see this kernel G1 and this kernel G2 corresponds to the two terms here in the right hand side. So in this way, our problem, and I'll write here because I'll come back to it, this is a coupled fixed point problem. So this is a coupled fixed point problem for the operator f. U equal f of u and v equal f of v and u. So this is the equivalent form of the system of the two differential equations. These are some details, how we get this, and what kind of functions, green functions, we are using here. If you are not familiar with this transformation, I would suggest you to read some of these papers. I'll put references. So this is the way we transform the differential system of differential equations into an integral form, into a system of functional equations. And here are all notations needed. So I want to say a few words about my philosophy of doing mathematics. I enjoyed when Professor Murthy spoke about the philosophy of doing mathematics. So I am evaluating myself, my own papers. Sometimes it happened to me, I take a paper I published 20 years ago, I just remember something about this paper. And I read it very interested. I said, let's say what I did here. And if I like it, in the sense is a pleasant reading, then I say this is a good paper. This is artistic impression. But I also ask for, in that paper, to have a clear statement of the problem, a clear statement of the new results, to have examples, as I mentioned, and applications. And I also ask for a very well documented paper. And sometimes, you know, it happens to any of us. I discover, I said, oh, this was the first time one notion or one result has been published. And after 5 years, 10 years, I discover this is not true. And so I changed the phrase. So I always says, it appears that the first, I don't risk to say this is the first, because we are not sure. So if it is well documented, it means this is no any new information about this result, then this paper was well documented. And also, I asked to a paper, not all my papers fulfill this this requirement to include open problems, to suggest to readers something to think about. So to be a starting point for some new directions of research. So if I evaluate these papers I mentioned before, I like them. Here it's okay, it's pleasant reading, it's quite well documented, the examples, the statements are clear, are open problems, but the applications, after a while, I realized they are not quite significant. So I'll try to show you exactly what happens. The precursors of this coupled fixed point theory are these two mathematicians. Lakshmikantam, I guess it's an Indian, famous. He was a famous Indian mathematician working in USA. He was also editor of nonlinear analysis for a long time. And his collaborator, they wrote some papers you can see from 1987. Then this Chinese mathematician also was interested on establishing existence theorems for coupled fixed points, also in a very good journal. And one of the best books in these subjects are the ones from Heikila and Lakshmikantam, published in 1994, about monotone iterative techniques for discontinuous nonlinear differential equation. If you are interested on this book, this is really useful because it is devoted to these monotone techniques. And not last, this paper by some Chinese mathematicians in 1996. It was a very interesting moment. In 2004, these two mathematicians ran, it's from Netherlands, a very strong mathematician. And Reurings is his PhD student, a lady. And they were interested to solve some problems, not in fixed point theory, but they were trying to find a theorem that should be solving their problem. And they were led to this, to write this paper and to state a fixed point theorem in partially ordered sets. And they were interested, actually, as the title suggests, to apply to matrix equation. They had some matrix equation, and no one of the methods they found in literature, let's say Banach contraction principle, other fixed points, could not be applied because they had some monotonicity involved in that problem. So they succeeded to find a very interesting theorem. I'll present you. Then two Spanish mathematicians, Nieto and Rodriguez Lopez, they continued this paper by Reurings. They applied to solve also ordinary differential equations, and the second paper is this one. And then, very soon, Bhaskar and Lakshmikantam wrote this paper, which was extremely successful in 2006, so 2 years later, 1 year later. So this, what did Lakshmikantam and his colleague? He just unified these these three theorems, actually. And what did Rahn and Reurings? They usually, in the Banach fixed point theorem, we have this condition. Let's say alpha. but for all x and y and x. So they changed this. They changed this and they have weakened the requirement, and I'll show how. And they combine another interesting fixed point theorem, which is in ordered sets, is Tarski fixed point theorem. Tarski theorem is, has an algebraic flavor, so it's in complete lattices. In a complete lattice, if we have a monotone operator, so Tarski theorem says we have, it has a fixed point. And Rahn and Reuring's unified Tarski and Banach fixed point theorem in this way. And how they did? So they consider on this space X a partial relation, and their idea was to ask this condition not for all x, y, but for all x and y which are in relation, which compare each other to the other. So this is their progress. And so that new theorem, which has a, how to say, an ordered and contraction type character, was very useful to establish existence and uniqueness results for various operators. And of course, it is possible to apply these kind of results to periodic boundary value problems and to other differential and integral equations. So here is the statement of Rahn and Reuring theorem. We have X a partially ordered set, so only partially, not total relation. D is a metric on X, and XD is a complete metric space. So this part, Professor Murthy said I can write here. I'll So this is coming from Banach fixed point theorem. This part, the other part is coming from Tarski fixed point theorem. So it is a very nice unification of the two fixed points. So if T is continuous and monotone, this is coming again from Tarski fixed point theorem, and this is coming to preserve the property from Banach fixed point theorem, because in the Banach fixed point theorem we know that any contraction is continuous, so it is necessary to have continuity. And the constant is here C. There exists a contraction coefficient C such that we have this condition. Here is for X in this relation with Y. So Y is less than or equal. He is not the usual inequality. Take care. This is the relation, the partial relation on the set X. Is not the usual complete relation, for example, on the real axis. And if also we can find an element x0 which compares to T of x0 in the sense x0 is less than or equal to T, or x0 is in this situation with Tx0, then the result is exactly the one from Banach fixed point theorem, and maybe I